We have seen what actors are and how messages are passed between them, but how does one go about actually writing actor systems? This is what we will look at in the following, and we will encounter a few other useful things to use in the Akka toolbox. When starting to design an actor application, it is helpful to visualize first a room full of people, and you have all these people at your disposal. You have your task which you need to solve, and what you need to figure out in the process is how to divide the task into subtasks and sub-subtasks so that every person knows what to do and there is not too much to do for any one of them. Since actors have fairly low overhead, you can create many of them, so consider this group of people to be of very large size for all practical purposes. As you know from organizing like a party or anything where people collaborate on, it is important to keep an eye on who will have to talk to whom and how much they will have to talk in order to fulfill their tasks. It is important to optimize the communication paths in an actor system just as it is in a human organization. There is one aspect of this comparison between actors and people which does not quite hold, and that is that actors, in contrast to people, are easily spawned and terminated. You can create as many of them as you want in the process of solving your problem, and they can be short-lived, just unlike people. As you go about defining the tasks of certain actors in your system and their role they play and the other actors they collaborate with, draw a diagram and mark down the communication lines between the actors and how they relate to each other. I will demonstrate this process now on a simple project. The problem which we want to solve is to write an application which, given a URL, it will go to the web, retrieve the document, check for links in it, and follow the links and repeat the process. Up to a certain maximum depth, of course, otherwise it would be boundless. And all links encountered in the process shall eventually be returned to the one requesting that this be done. How would you solve this with a bunch of people? There will be one actor, which we call receptionist, and this one is responsible for accepting incoming requests. These will come from some external client. This receptionist is a person who will just have the responsibility of accepting a request, noting down that it shall be done, noting who was the client, and then telling someone else to do the real job. When traversing the web, we will encounter many links, and there might even be cycles. So when we see a link which we have already visited, we need to stop there because otherwise we run in an endless loop. It is best that we assign one person to the task of one such traversal because that person will remember what has already been visited and what not. Translating that into an actor, let's call it controller. This controller will need help because its main job is to remember what was visited and what still needs visiting, but it would be better if we had someone else to do the actual visiting of a link and to extract the information which we want. So let's put in another actor which we call getter. Getter is a rather simple one. It will just go look at one URL, retrieve the document, extract the links which are in there, and then tell the controller what it found. The controller can then spawn other getters to visit the new links and so on. To recap, let us now put in the messages which will be exchanged to achieve this. The client sends a GET request for a URL. The receptionist will create a controller and send it a check for a given URL with a certain depth, because we do not want to do this in a boundless fashion. The controller will then tell the getter, to retrieve what is at that URL, and the getter will then reply with possibly multiple links, and then finally a done message, so that the controller knows that this getter has exhausted all which was found at that URL. All links which are found in the process should be treated as quickly as possible, and they can also be retrieved in parallel. So there will be multiple getters which perform the subsequent checking of the links in parallel. The controller will have to keep track of which URL was encountered at which search depth. So let us say this comes down at depth 1, then the links come back at depth 1, but when they are checked by the next getter, they will be at depth 2, and so on. It is best to keep this state traveling with the message, so that this request contains the depth and the responses contain the depth, freeing the controller from having to remember all of this. Once the depth is exhausted and all getters have sent their done messages, the final result is communicated to the receptionist. The receptionist was the one who kept track of which client requested which URL, and it will send back the appropriate response to the client. This is the whole process which we will implement in the following. What we will do requires the use of some web client. I will be using the async HTTP client library as given in this artifact here. Then we need to write a getter for processing the body which was retrieved. Then we step up one level to write the controller, which takes care of the getters and all links encountered. And finally, we will think about the receptionist and how that manages the controller. Let us start with the most simple example, which is also given at the top of the documentation for async HTTP client. First, we create an instance of this class and store it away. This client is able to perform multiple requests, and it will cache connections to servers, being quite efficient. The client will be used by the get method. We give a URL as a string, and we expect back the body again as a string. So we call client prepare get for the URL, execute. This gives us back a future, but not a Scala future, on which we call get, and this will wait until the response is there. So we have the response here to deal with. Then we check the return status code. If it is not an error code, then we look at the first 128 kilobytes of the body and give that back. Otherwise, we reply with a bad status, and the reply in a synchronous method like this one of a bad result is done by throwing an exception, as we know. This looks very simple, but it is also problematic. The problem is precisely here. Here we block until the web server has replied and given us the whole body, and we have stored it in memory. If we, for example, use this method from an actor, then this actor will be blocked. It will not be able to execute anything else until this finishes, which means that during this time the actor is deaf to other requests. For example, we will not be able to send it a request to cancel the operation. The other problem is that blocking in this fashion wastes one thread on our machine, and in the virtual machine you can have a few thousand threads, but for sure you cannot have millions of them, and you can have millions of actors. So there is a mismatch, and we should always think that we should not waste threads because they are a finite resource. How do we fix this? Well, we still use the same client, and as the name implies, it is an async HTTP client, so it is capable of performing the operations in a non-blocking fashion. First, we do the same thing, but we stop at the execute. This gives us back a future. We want to adapt this into a Scala future, so we construct a promise, as you have seen 2 weeks ago. The future returned by async HTTP client is not a Java util concurrent future. It has some added functionality, namely that you can add a listener. When this future is completed, this listener, which we register a runnable on, will be run. So this gets executed. So when we call f.get in this code, it will not block because we know that it has been completed. Running this runnable will need an executor because it is a task which is to be run asynchronously, and that is a common theme that you will need a thread pool in the end on which to execute these tasks. In the end, we need to return a future, and you get the future from a promise by saying p.future. Async HTTP client is a Java library using Java and its own futures. So what we have done here is in essence a mapping from the listenable future of async HTTP client to Scala's futures. I have included this here to demonstrate a common pattern. If you have an event-based source for something and you want to wait for a single-shot event like in this case, it is best to wrap things in a future and expose that as an API. Then if someone needs a synchronous version, they can still await if they really need to, but being asynchronous as the default is good for reactive applications. That was the main lesson to be learned here. A reactive application needs to be non-blocking and event-driven from top to bottom. If there is one blocking piece in it, it will infect all other code which tries to call it. Therefore, watch out and try to use asynchronous libraries where possible. Now that we have the ability to retrieve documents from the web, we just need to find the links in them. This entails parsing the HTML of the body strings that we have here, and for that purpose we use a Java library called JSoup, which we use from this artifact and import here. Parsing a string of HTML text yields a document, and a document is a structured representation of the HTML tags, which we can query. In this case, we look for all anchor tags which have an href attribute. We then grab an iterator over the set of these potential links to visit and convert it to a Scala one using the Java converters utility. And then this for expression yields for every link the absolute URL that is contained in the href attribute. And that is then the iterator of URLs that gives us the further sites, further links to visit. With these preparations, we can write our first actor. This is the getter, which gets the URL to visit and the depth at which this is currently happening. The first thing that this actor needs to do is go to the web using the web client and fetch the URL. This gives us back a future as we have programmed, and when this future completes, it can either be successful or a failure. In order to make the actor aware of this, we need to send it a message. That's all actors do. So in case of a success, we retrieve the body string that we obtained and send it to this actor for further processing. If it is a failure, we also send it to this actor wrapped as a status failure message. This pattern is so common that Akka includes it as the so-called pipe2 pattern. When you import akka.pattern.pipe, you can say future.pipe2 and then some actorref, usually the self address of the actor. But we know using Scala's syntax we can make this even a bit more nice by removing the dots and the parentheses, and then this reads like normal English. Web client get URL pipe to self is a recipe for what this actor does in the beginning. Within this, we have two steps that are executed asynchronously. The get needs an executor, and the pipe2 needs an execution context to run a Java listenable future and a Scala concurrent future, respectively. These execution mechanisms are picked up implicitly from the surroundings, which we provide here by saying implicit val exec, which is an executor and an execution context. And it just so happens that the context.dispatcher, so the machinery that runs the actor itself, can also execute futures, both Java futures and Scala futures. So this implicit value here is used in both places to make the futures run. Now that we have arranged for the data to arrive at the actor, we need to write down its behavior, what shall happen in this case. If we get a string, which is the body, then we use our findLinks method to get an iterator of all the links, and for each of those links, we send them in the message. Context has another nice method, which is called parent. Remember that every actor was created by exactly one other actor, and that is its parent. We can access it like so, which gives us an actor ref. And we send the message to check the new link we found at the depth which we have been told. Once we have communicated all the links back to our parent, we stop, which means sending the parent a done message and stopping ourselves. In case of a failure, we just send the done right away and stop. What we have learned here is that actors are run by a dispatcher, which is potentially shared among multiple actors, and this dispatcher is also capable of running futures. The next actor which we'll be writing is the controller, and in that one we would like to log the progress which is made. Logging is also something which is handled by Akka. There are many flavors to solve this particular problem and many frameworks out there. The solution which we chose is specific to actors in the sense that it is focusing on not blocking the entity which wants to do the logging. The obvious way to achieve this is not to perform any I/O like writing to the disk or to the network directly, but to pass that off as a task to a dedicated actor, because we know that sending to an actor is a non-blocking operation. You can set the overall log level with the setting akka.logLevel. I put it to debug in this example. You can conveniently use the logging by extending the actor trait with actor logging, which will give a log method that returns the logger for this actor. The source information provided by this logger will contain the actor's name. So there you have a case why it is very important that you properly name your actors. Here we simply log a debug statement that we received a certain message given here. There is a very simple syntax using this pair of braces to denote something which needs to be put in. Without further ado, we will look at what the controller now does. Remember, the job of it was to accept the check messages for certain URLs, and once everything is done, to send back the overall result. The result needs to be collected somewhere, and this is the cache here, which is a set of strings, and the strings will be the links which were visited. Whenever a check request arrives, we log it at debug level to see the progress. Then, if the cache already contains the URL, we don't need to do anything about it. Or if the maximum depth is 0, we don't need to do anything about it. But otherwise, we need to create a new getter, tell it about the URL to fetch, and decreasing the depth by 1. This is created using actor_of, which gives back the actor ref, and we need to keep track of all the children we have created. This is kept in the second set named children up here, which is a set of actor refs. Finally, this URL will have been visited, so we add it to the cache. The getter which we have just created will go to the web client, ask it, retrieve the document, get back the links, and will send other check requests at depth -1, because that's what we told it to do. And at some point, it will be finished, and then it will send a getter done. At this point, we remove it from the children set. And once no getter is running anymore, we know that the whole process is finished. So we tell our parent the result. The result is just the set of links which we have encountered here. At this point, it is important to note that we are sharing the cache here. If we would have used a val cache with a mutable set instead, then sending that to the parent could have disastrous effects. For example, this controller might be used to process another query, keeping the cache. Would be a valid use case, but then the result which had been sent back to the parent points to the same set, which is mutated by this actor, and then the other actor will be confused as to what the contents of the set are. It is much better to prefer using variables here, which point to immutable data structures. This way they can safely be shared, as is done here. And that is the third point which we have encountered on our journey, the third lesson we learned. The controller and getter which we have written so far play well together, as long as the web client always yields a result. But what if, for example, a web server takes really long to respond or does not respond ever? For this we need to foresee a timeout. A simple possibility is to use another function of the actor's context, the capability to set a receive timeout. This receive timeout is a timer which is reset or restarted after the processing of each message. So whether we get a check or a getter done, or even this receive timeout, once we have processed it, the receive timeout will be reset again to 10 seconds. When it expires, we get, namely, this receive timeout object here. And in this case, we tell all our children to abort. Of course, we need to code this functionality in the getter as well. That we can see here. We add a new case abort, in which we just stop. In order to support services like the receive timeout, Akka includes a basic scheduler. The focus of this scheduler implementation is on supporting a very high frequency of scheduled tasks, but also a very frequent cancellation of these. The flip side of this is that it is not terribly precise. Its main use is to schedule the sending of a message to an actor at a future point in time, which is the first variant given here. The object which is returned from schedule once is a cancelable, which you can use to cancel the task, but be aware that there might be a race condition between the task firing and you canceling, so it is possible to receive the message in the target actor after cancel has been called. This is usually not very problematic, because often it is the actor itself which schedules the message it wants to receive later, and then the actor can just store away the knowledge that it has cancelled the task and can then ignore the message should it arrive nonetheless. There are two other variants, this one more for Scala and this one more for Java, for running an arbitrary block of code after the delay. But these two methods should be used with care. We could have implemented a timeout in a different fashion. For example, if we wanted to have a timeout which fires 10 seconds after the controller starts and not 10 seconds after the last message was processed, then we might use the scheduler. The context gives you access also to the whole system. The system is the container in which all actors run, and it contains many services, among others also the scheduler. And you can ask it to schedule once in 10 seconds that this block of code runs. Now we say that after these 10 seconds we want to tell all children that they shall abort. What is the problem you see with this code? Is it that it does not compile, or is it not thread safe, or will the scheduled code simply not run? The right answer is that it is not thread safe. And the reason is that the scheduler will run this code, and it will run outside of the context of the actor. It will not be run by the actor, it will be run by the scheduler. And this means that there is no protection that this code might run concurrently with the actor processing the next message. And both of these codes, then the actor and this block, access the shared variable children, and they try to modify it or try to read from it. And that could have unpredictable results if there is no proper synchronization. And the trick was that actors encapsulate their state such that no synchronization is needed. This is a plain var, and we don't take any locks. It would be nice if the compiler could tell us about this problem and give us an error that we did something wrong here. That is unfortunately not yet available. Or it would be nice if the actor could somehow magically know that this code shall not be executed by the scheduler and refuse to run it. But that also is impossible to realize. So this is why you need to manually make sure that this problem is not one which you invite into your code. So how do we do this properly? This is why I emphasized most the first variant of the schedule once method, which takes, besides the delay, an actor ref and a message. And the scheduler then makes sure that the message is delivered after the delay has elapsed to the actor ref, and we get it here in the behavior. Here we can safely access the actor's state, and in this case tell all children to abort. Similar issues can occur if you mix futures and actors. As an example, we have here a simple cache actor, which when it gets a request to get a URL, it will look into its cache, which is a variable here, and if it finds something, it will reply with the element in there. Otherwise, it will have to go to the web and actually fetch the document. As we remember, web client getURL returns a future, which we can use for each upon to act when the body has been received. And in that case, we just update the cache and reply to the sender. The first problem is exactly like in the scheduler case, this access to the cache, which happens from outside of the actor's scope, namely in the scope of the callback on the future. And if the actor runs at the same time, then both may access the cache variable and there might be clashes. Fortunately, we know how to fix this. So we take this future, we map it, and pipe the result to ourselves. And this result will contain the body, the URL, and the sender of the original request in one package. And once we get it here, we can safely update the cache and reply to the client. But this actor contains another problem. The transformation described by the map operation on the future runs the code which you give it in the future. And that means that the sender will be accessed in the future. This is problematic because sender is giving you the actor ref, which corresponds to the actor which has sent the message, which is currently being processed. But when that future runs, the actor might do something completely different. Therefore, we must cache the sender in a local value. And when you reference this local value in here, then the closure which is formed by this function literal will contain the value itself and not the recipe how to obtain it. So it will not call the sender method. So the fourth thing we learned is that we should make sure that we do not refer to actor state from code which is running asynchronously, for example, using the scheduler or in future combinators. The last actor which we need to create is the receptionist. In this implementation, the receptionist always will accept requests, but it will make sure that only one web traversal is running at any given time. Thus, the receptionist can be in two states. It can either be idle, waiting for the next command, or a command can also already be running. When when we get a request, we need to start the traversal and switch to the running state. In the running state, when we get a request, we cannot execute it immediately, so we append it to some queue and keep running. When we get back a result from the controller, we need to ship that back to the client and then run the next job if there is one. If there is none, then we go back to the waiting state. In our formulation of the two behaviors, we will need helper methods, and the first one is run next, whose job it is to pick the next job and run it. Here a job is a tuple of a client, actor ref, which has sent the request, and the URL which shall be visited. When the job queue is empty, then there is nothing for us to do, and we go back to the waiting state. Otherwise, we need to instantiate a new controller, send it the work, which is to check this given URL at the head of the queue, and here I hard-coded the depth of the search to 2, and then we are in the running state with this queue. As always, it is a good idea to name actors. And these are controllers, so we name them C something. But there is one condition, you may remember, that actor names need to be unique. So we cannot call them all just controller. To facilitate that, there is a variable request number which gets incremented every time we execute run next. That means that during each run of this method, this number will be unique. This number could also be used, for example, for statistics purposes, so that you can ask the receptionist how many requests it has already processed. The second helper method is used to enqueue a job. Given a queue, which is a vector of jobs, and a new job, we simply check. If the queue has a certain size, we limit it to 3 here. Then we immediately reply with a failure and stay in the current state. Otherwise, we append it. Now we can plug all things together to show the two behaviors in their full glory. First, waiting. Once we get a URL to check, we become run next of a queue with this one job in it. Eventually, the controller which was spawned in here will send back a result of links. We look at the queue head to find the job, extract the client, and send the result with the links and the job URL back to it. Then we stop the controller because we will want to use a new one for the next request. The next request is obtained by using run next with the tail of the queue. This might be empty, then we would go back to the waiting state. Or there might be something left, and then we stay here. If in the running state a GET request is received, then we simply enqueue the job and stay running as we said. During our journey of designing an actor system, we have learned how to do that, but we have also encountered the following valuable lessons. First of all, a reactive application needs to be non-blocking and event-driven from top to bottom, meaning that you should strive for the use of only asynchronous libraries where possible. Asynchronous libraries often have use for an executor or thread pool, and we have seen that the dispatcher which runs actors is very useful also in that regard. The third point was to always prefer immutable data structures because they can be safely shared and there is no problem in sending them across thread boundaries. The fourth point was to always prefer context become to model different states of actors and to keep the data local to the behavior where that makes sense. I have shown you some examples of where a deviation might be useful. If in doubt, always code both ways and compare them and choose the one which is more readable, more clear, or more concise, and also consult with your colleagues who will have to maintain that code. And the fifth and very important lesson is, do not leak the actor's internal state to code which runs asynchronously, because that breaks the actor model encapsulation. we have assembled all the pieces for our program. Now we also want to see it in action. For that, I have created a main actor, as you have seen before, which will run it. The first it will do is to create a receptionist, and then it will send a request to this receptionist to check a well-known website for links. The reply will be received here, and it can either be a positive, in which case we take the set of links, convert it to a linear structure from a set, sort that one, and convert it to a string by saying results for this URL, and then on each line is one link. If we get a failed result, we print failed to fetch. Finally, we want this application to terminate if no more messages are received after 10 seconds. In that case, we get the receive timeout and stop the program. It should be noted that the async HTTP client in here has some resources which it needs to shut down for the JVM to properly terminate. I have created a run configuration as before using the main class akka.main, and if we run it, we will see the output. Results for http www.google.com. We see a number of links were found. The search depth was 2, if you remember correctly. So first it was going to that. I can tell you I tried it. This gives you a redirect to google.com/ and then some very complicated cookies. And if you follow that one, you get the actual search page, which you see in your browser when you open it. And that contains a lot of links, some international links. I have a German set browser, and I'm currently in Switzerland. So you see here all what is on the front page of Google. Now let us try to give the receptionist a bit more work. You may recall that we limited the queue it keeps to the depth of 3, meaning it will start processing the first request, then it will queue these 3, and it should fail on the 4th one. Running it again, we see the first failure here. The 4th request was rejected. Then we see the result for the first one, which we already know. And after that, we have the results for /1, 2, and 3. These are URLs on which there is nothing to find on Google, so they turn up just the link which we gave initially as visited. This program is of course no proper link checker. You would have to augment the functionality, especially in the getter, to make it right. But I'm sure this can serve as a good starting point if you would ever choose to implement one.